Welcome to Secret Squared. I'm Cassie Secret. I'm Megan Secret, and today we're going to continue our series on factoring, and we're going to do factoring by difference of squares. So let's dive in. So factoring by difference of squares is one way that you can factor. For us to be able to use this method, there's three things that have to happen. So the very first thing that you have to have is we need to have two terms. A very common math term that you might hear is this is actually also called a binomial. In a later video, we're going to talk about something called a trinomial and how to factor that. So one, we need two terms. Second thing is we can't just have two terms. We need it specifically to be, we need one term minus the other term. If it doesn't have that minus, it's not a difference, which is why we need that. Yep, so again, because it's a difference, you have to have that subtraction. And the last thing we need is, it is a difference of squares. We have the difference right here as our subtraction. Now we need the squares or those perfect squares. So we need both terms that do show up to be perfect squares. So for that, when you're talking about a perfect square, for example, 25 is a perfect square because it can be rewritten as 5 times itself. So it's just a little reminder of what it means when we're talking about looking for something that is a square. So from there, just looking at a couple examples of when we can actually use difference of squares and when we can't, because it doesn't work for every problem. So for our first little example, if we're looking at something like x squared minus 9, now I see two terms. Terms are separated by pluses and minuses. So that's a check for the first one. I have two terms. And I do have that subtraction sign. So check, it is a difference, but you now have to check it's a difference of squares. So both of them have to be perfect squares. Now, x squared, if you have that even exponent, that means it's a square or a perfect square. And the 9 that we have is also a perfect square because 9 is 3 times 3. So for this one, I'm going to put a little check. We could, in fact, use difference of squares. If we were to make a slight tweak to that, so let's say we had x squared plus a 9, we still have the same exact terms. The difference is we are not subtracting, we're now adding the 9. Because of that, it is not term minus another term, so it is not a difference of squares, or we can use a difference of squares because of that adding. So again, it's just really important to know and recognize when you can actually use difference of squares and when you can't. Now, another one that we have to look at, if we have something like this, we have 2x squared minus 25. Now, two terms, I have two terms that are separated by that minus, so that's a yes. I need it to be subtraction, and I do have that, so check, I'm good on that. And the last one is I have to have perfect squares, which this looks like it might work because I have x squared and I have 25, which 25 is a perfect squared, 5 times 5. But I have that 2 in front, and 2 is not a perfect square. So that actually means that this example is not going to work. So even if a lot of the pieces of it look like it does work, if there's one that doesn't work, like we're not subtracting, we have 3 terms instead of 2 terms, or both terms are not perfect squares, or even if one piece isn't a perfect square, that ruins everything. So now we're going to look at what the rule is for when we factor by different squares. So normally what you're going to see is still the same thing, the two terms being subtracted. And for this, we're just going to do generic variables. So let's say it looks like x squared minus y squared. It looks a little bit different because there's no numbers, but we have something squared minus something else squared. So this is just a more generic way of writing it that's going to allow us to make a general formula. Now, the way that we like to do it, we found that finding ways to break down the problem and actually have a helpful way of writing it helps you to remember what the rule is. So in this case, what we're going to do is when we're going to break it apart, so when we're talking about difference of squares, squares are always going to be something that times itself gives you that perfect square. So 81 is a perfect square because 81 is 9 times itself. 64 is a perfect square because that's 8 times itself. Now, we're actually going to be using that fact about perfect squares to help us break this up. So when we're talking about x squared, I'm going to use a little, looks like an upside down V. If you've ever done stuff with prime factorization trees, this should look pretty familiar. When we're talking about x squared, we can break that up into x times x. Because if you were to multiply these together, just a reminder, you would add those invisible exponents, and that's how you'd get back to x squared. You can do that same thing with the y squared. Y squared is really the same thing as y times y. I will say this is a negative in front of the y squared. We are looking at just a positive y squared. Y times y gives you a y squared. But then from there, what we want to think, and this is a really helpful tool that I use to remind people of a common error that people make when they're breaking this up. When we're breaking up the y squared, we are just thinking about it without the negative. It's y times y. But then after the fact, and we're actually going to see in the formula, we're going to end up having a negative show up, and it's actually because of the minus here. So what we're going to do is we need to make one of these y's a negative. It doesn't matter which one you get to pick. I tend to make the first one a negative, but it's not going to change your answer. The reason that we're writing it this way is now everything that's written underneath gives you all of the pieces that you need to write your answer. And from here, we're going to kind of pair things up. So I'm going to grab the first x and the first y, or in this case, it's a negative y. And what we end up with is when we factor things, we really want things to be multiplied together to give us this original part. We're going to have something times something else. In this case, we're going to grab those purple parts. We're going to grab the x minus the y, and that is going to go in our first set of parentheses. After that, we're going to go ahead and take the other x and the other y, and this is going to be x, and that y, that second y, is a positive y, which is why we're going to put a plus y. And that's why in the very first one, when we took that x and the negative y, that's why I tend to like putting that minus. That way you actually remember to put the minus when you're writing it out. And note, order doesn't really matter. You could have written this as x plus y times x minus y. As long as one of the y's is negative and one of the y's is positive, you're in a good spot. And then just a little note to make sure that this isn't confusing people. When we're grabbing the x's and the y's, I just feel like it's a lot cleaner to take the first x and the first y, and then to take the second x and the second y together. You don't have to do it that way. You could have taken the first x and the last y, and then done the inside ones together. You're still going to get the exact same answer. So for our first example, we are going to have 16x squared minus 9. First things first, we can use the difference of squares. There are two terms we are subtracting, and both of them are perfect squares. 3 times 3 is 9. This part is a perfect square, but this might not be as obviously a perfect square as the second term. You can just think about breaking up and looking at the number and the variable separately. 16 is a perfect square because it's 4 times 4, and x squared is a perfect square because it's x times x. Now, as we get into actually breaking this up, we went ahead and we put our formula or our rule up above just for reference as we're going. So now, same thing as the last page, we're going to break down this into things that multiply together to give us the 16x squared. Same thing with the negative 9. So looking at the first term, which again looks a little bit different since there is that coefficient that's not a 1, we can start with 4 times 4 gives us 16. So each of those branches will get a 4. But 4 times 4 does not give us 16x squared, so we also have to deal with the x squared. We need an x times an x to give us the x squared, and we can double check 4x times 4x gives us the entire 16x squared. And then looking on the right side, we have that 9, really negative 9. Ignoring the negative for a second, 3 times 3 gives us 9. But because we want it to multiply to a negative 9, we're going to make one of the terms negative. It doesn't matter which, but negative 3 times 3 does give us a negative 9. Yep, and honestly, breaking it up this way is like the very key first step, and then you have all of the pieces that you need for your answer right there. So, as Megan had said earlier, we know when we're factoring, we want to rewrite this all as a product. So I'm going to start by taking one of the 4x's and one of the 3's. Doesn't matter which one. I'll take the ones on the left. So I have 4x and it's a negative 3, so I'm going to put minus 3. And then I'm going to grab the 4x and the other 3, and that'll be 4x. And because that 3 was a positive, it's going to be a plus 3. Now, a very important note that I want to make for factoring in general, and this is going to end up going for pretty much every single type of factoring that you're ever going to see. You actually always want to check for a GCF. Now, a GCF is that greatest common factor. We actually already covered that in a previous video. Looking for a GCF always needs to be the first step when you're factoring. Now, in this case, I didn't show it because there actually was a GCF of 1, which isn't going to affect your answer. You wouldn't have to factor that out. But it is something you want to look for going forward because there are some problems where you take out a GCF and then you do difference of squares. So for our next one, and keeping in mind that GCF, we're going to look at 16 minus x to the fourth. So first things first, there's no GCF between these two. They actually have a GCF of 1, just like the last one, so we don't have to take anything out. But we're now going to do the same steps. We're going to break down the 16 into two things, then multiply 2 16, which is a 4 and a 4. And then on the right side, we have that negative x to the fourth. It is weird because in all of our previous ones, we've had x squared is the biggest, and we haven't had a negative minus a variable. Over here, ignoring the negative for a second, we have x to the fourth. Because of the product rule, we can break up x to the fourth into x squared times x squared, because when you multiply these together, we add the exponent. So we have 2 plus 2 does give you a 4. And then because we want it to multiply to something negative, we're going to make one of those x squareds negative. Yep, and then from there, we're going to go ahead and write it out. Now again, we want to factor it, and it's going to end up being written as the product of something. I'm going to go ahead and I'm just going to take the first 4 and then that first x squared. So it's going to be 4, and since it's a negative x squared, do minus x squared. And then the next one, I'm going to take the other 4 and the other x squared and put those together. Because that x squared is positive, I'm going to go ahead and put a plus. Now for this one, just a quick reminder, we said this on the last slide, but these parentheses, you could have had them swapped. It is totally okay if you put a plus first and then the negative after. It just totally depends on however you want to write it. And then from there, we have one last step. We've actually factored it, but looking at both the individual chunks, the left whole set of parentheses is actually another difference of squares, so sometimes it can be hiding in there. We can do the same steps we've already done. So I'm just going to do this right in here. We have 4 is 2 times 2. And looking at the x squared, that's an x times an x, because we wanted to multiply to a negative x squared and make one of them negative. And then following the same steps where we grab 1, 1, 2, 1 negative x, and then another 2 and an x, we're now going to end up with 3 sets of parentheses instead of just 2. So this yellow chunk becomes a 2 minus x, and that came from our green terms. And then we end up with a 2 plus an x from those purple terms. And then that blue chunk, the 4 plus the x squared, the 4 and the x squared are both perfect squares, but we are not subtracting them, we're adding them. So we can't factor that any further, and it's going to stay the 4 plus the x squared. So for this example, it's really showing you that sometimes when you're factoring, you need to be on the lookout because oftentimes it's a multi-step process where it's not just doing one thing, a lot of times it's doing several. And just to kind of say again what Meg already mentioned, that first one, we were able to break it up again because it had that minus, it had 2 terms, and they were both perfect squares. And the second one, we were not able to break up because the plus, you cannot do a difference of squares. So that's going to be our example, or our answer for the last one. And then just to be clear, our answer for the top one, neither of them had a GCF, so we didn't have to worry about taking that out. So for the last 2 examples, we had both of them had a GCF of 1, but going forward, we'll really want to double check and see if we do have a GCF. So for instance, this example, we have 2x squared minus an 18. Both the terms do not have a variable, so there's no variable in common, but this term has a 2, this has an 18. They're both even, so we actually end up with a GCF of 2. And just a little note that I want to make. For this problem, if you did not look for a GCF and you were only looking for difference of squares, you would probably say, hey, I can't do difference of squares with this because 2 and 18 aren't perfect squares. And that's absolutely right. That's actually why it's extremely, extremely important you look for GCF, because if you didn't find this GCF, you would actually think that you couldn't factor this, but you absolutely can. So with that GCF in mind, we are now going to divide out that GCF. So we're going to divide both terms by 2. So we end up with right here, those 2's are going to cancel out, so we end up with just the x squared. And then we have negative 18 divided by 2 gives us a negative 9. So there's going to be our difference of squares. But whenever we're factoring with GCF, we have to double check that we put that GCF on the outside of those parentheses, because technically x squared minus 9 is not the same thing as what we started with. But if we were to multiply out this 2, then this is exactly what we started with. Exactly. And then, so from there, whenever you're factoring, you want to keep looking at what you have inside the parentheses and see if you can factor it some more. Like we saw on that very last example, sometimes you can keep going. In this case, what's on the inside, we can do difference of squares with. So we're going to go ahead and break it up. X squared, you can break that up into x times x. And for negative 9, think about, ignore the negative. 9 is just going to be 3 times 3. And because we have to multiply to get to negative 9, one of your 3's has to be a negative. You can pick either one. And then from here, we're going to do the same steps we did earlier. The only difference is we have that GCF out in the front, and that GCF is going to stay in the front. So we're still going to have the 2. And now we're going to have 2 separate things multiplied together. We're going to grab one x and one of the 3's. Now we have an x minus a 3. Again, it doesn't matter which order you grab the x and 3's in. I just like to grab the left one from each. And then we have the other x and the other 3. So now we're going to have an x plus a 3. And double checking. Sorry about our dog. And double checking, we can't factor those anymore. So this is going to be our final answer. So for our last example, we have something that's a little bit more difficult. We have an x cubed, and we have 2 different variables in this right term. It doesn't really look like a difference of squares, but that's why we always need to check for GCF first. So looking at the coefficients, we have a 3 and we have a 27. 3 is actually going to be the GCF of those 2 numbers. 3 is the biggest thing that goes into 3 and goes into 27. And then looking at the variables, for that variable to show up in the GCF, it has to show up in both terms. In this case, we have x's in both terms, and then we're going to grab the lowest exponent of them. In this case right here, this x does not have an exponent, so we're going to assume it's really an x to the first. So we're going to have just an x to the first, or one x in that GCF, because we can only take one x out, because we can't take any more than one x out of this term because there's not any more than that. And then for this one, there is not going to be a y at all in your GCF, because there is a y, there are 2 y's in the last term, but there's no y's in the first term. So this is going to be our GCF. Just like we were doing before, we need to go ahead and take or divide that GCF out. Now, when you're doing this, go one fraction at a time. 3 divided by 3, that's going to get you 1, which you don't have to put in front. And then x to the power of 3 divided by x, that's really going to be using our quotient rule, which you're going to subtract the exponents. 3 minus 1 will get you x squared, which this is already looking better because now I have something squared, which seems like it's going to be better for difference of squares. Then the next one, 27 minus 3 is 9. Now, be careful, we still have that minus there, which is good because this is going to allow us to have a difference for the difference of squares. Our x terms, those are going to cancel out because they're the same on top and on bottom. That y squared is just going to stay the same because there aren't any y's on the bottom of the fraction to interfere with it. So we'll keep that y squared. And whenever you have a GCF, every single time you need to take it and include it in the front of your parentheses, because really we need to have this to make sure that the meaning of what we have after we factored is the same as the meaning of what we started with. So from here, it looks, again, a little bit different since we have 2 different variables, but we do have 2 terms. We are subtracting those terms, and x squared, 9, and y squared are all perfect squares, so we can do a difference of squares. So we're going to break down each of the terms just like we did for all of the other questions. We have x squared is really just an x times an x. For the second term, again, it's different because we have that number in the front and the y squareds. We can start with 3 times 3 gives you 9, and that deals with that number in the front. And then, like the x squared, we have a y squared, which is really a y times a y. And since it's a negative here, or we're subtracting that term, and let me make sure it actually looks like a 3. There we go. We're going to make one of the terms negative. Doesn't matter which, we'll just pick the first one. And from here, we're going to make the same groupings. So we're going to grab the first of each, so the x and the negative 3y, and we can rewrite this. And again, our goal is always to have two sets of parentheses, or two things multiplied together. Now we have the x minus the 3y. That came from all of our yellow. And now we're going to grab the last term standing. We have the other x and the other 3y. That's going to go in the other term. And in this case, we have a positive or a plus 3y because that 3y that we grabbed actually is a plus or a positive. Because a negative times a positive gives you that negative term. And since we have the GCF out in the front, that's our final answer. Thanks for watching! If you enjoyed this video, please like and subscribe. If you have any other topics you want us to cover in later videos, leave us a comment below. We'll see you next time!